Hello everyone, welcome to Computer Organization and Architecture class. In this unit, we will talk about pipelining. The flow of instructions through a pipeline follows the 5 steps in the fetch-execute cycle. A pipelining can be considered as an assembly line where the assembly process of the product is broken into several steps. To maximize the efficiency, every step in the assembly process should use the same amount of time. CPU designer borrows the idea of assembly line and designs pipelining approach to execute instructions in the fetch-execute cycle. After the instruction fetch unit finishes its task, the fetched instruction is handed off to the decode unit. At this point, the instruction fetch unit can begin fetching the next instruction, which overlaps with the decoding of the previous instruction. When the instruction fetch and decode units complete their tasks, they hand off the remaining task to the next unit. That is, the operand fetch is the next unit for decode. The flow of control continues until all units are filled. Although it takes multiple steps to execute an instruction in this model, on average, one instruction can be executed per cycle as long as the pipeline stays filled. As shown on the screen, the frequency of occurrence of instructions in a mix of programs written in a variety of languages. Nearly half of all instructions are assignment statements. Interestingly, arithmetic and other more powerful operations account for only 7% of all instructions. It is worth noticing that approximately 1 in every 4 instructions is a branch if. However, the pipeline does not always stay filled. The reason is that we cannot fetch the instruction that follows a branch until the branch completes execution. Thus, as soon as the pipeline fills, a branch is encountered, and then the pipeline has to be flushed by filling it with no operations. These no operations are also known as pipeline bubbles. A branch may have negative impact on the pipelining execution. Branch prediction techniques are developed to reduce the change of pipeline flush. As shown on the screen is a 2-bit branch predictor, which is a state machine with 4 states. That is, strongly not taken, weakly not taken, weakly taken, and strongly taken. When a branch is evaluated, the corresponding state machine is updated. Branches evaluated as weakly not taken change the state to row strongly not taken, and branches evaluated as weakly taken change the state to row strongly taken. The advantage of the 2-bit counter scheme over a 1-bit scheme is that a conditional jump has to deviate twice from what it has done, mostly in the past, before the prediction changes. For example, a loop closing conditional jump is mispredicted once rather than twice. The efficiency of a pipeline is analyzed as shown on the screen. Assume a processor has 5-stage pipeline. If a branch is taken, then 4 cycles are needed to beflush the pipeline. The branch penalty B is thus 4. The probability PB that a particular instruction is a branch is 25%. The probability PT that the branch is taken is 50%. When the pipeline is filled and there are no branch, then the average number of cycles per instruction CPI, no branch, is 1. The average number of cycles per instruction when there are branches is as shown in the equation on the screen. A cycles per instruction branch can be substituted as highlighted in the red rectangle, and thus we can rewrite it as CPI average equals 1 plus B times PB times PT. The execution efficiency is CPI no branch divided by CPI average, which is 67%. When we estimate machine performance, the measure that is generally most important is execution time, T. We use speed up, S, to describe the impact of performance improvement. Speed up is defined as shown on the screen, where TW0 indicates the execution time without the improvement, and TW indicates the execution time with the improvement. For example, assume we want to estimate the speedup obtained by replacing a CPI have an average CPI of 6 with another CPU having an average CPI of 2, with the clock period increased from 50 nanoseconds to 100 nanoseconds. Therefore, the execution time without an improvement is 6 times 50, and the execution time with the improvement is 2 times 100. After plugging in into the equation, we can obtain the speedup S is 50%. Any questions?